So what we're going to be talking about now in these video notes are objects that are falling. So think about an object that you've dropped, and then based on what happens with that, we are going to actually derive and talk about that physical scenario. So anything that's dropped in our physical universe where air resistance is neglected, and this is important, air resistance is neglected, then that object is said to be in free fall. And to be in free fall means that the only agent acting on an object is the Earth. So if I were to draw a free body diagram of that, then I would see that the only thing that I have providing a force on an object that is in free fall is the Earth. And that's it. And those objects then are said to be in free fall. Now, in this case, the acceleration of the object is constant and equal to a free fall acceleration, which in physics is denoted by the letter lowercase g, and has a numerical value near the surface of the Earth of 9.8 meters per second squared, which that number hopefully looks familiar because remember when we were converting between mass and weight, that was the value that came into play. Interesting. It's like the Earth is constantly applying 9.8 newtons per kilogram, causing an object to accelerate at 9.8 meters per second squared. Weird. Or if you want to do imperial units, 32 feet per second squared and directed downward. So that's objects in free fall. Those are the numbers that we need. When we refer to a freely falling object, we're not necessarily referring to an object which has been dropped. So an object doesn't have to be dropped to be in free fall, but to any object which is under the influence of the force from the Earth alone. Force from the Earth alone. So if the Earth is the only force on the object pulling it downward, then we would say that that object is in free fall. When substituting the acceleration due to gravity, which is what we call g, the free fall acceleration, into any equation, the sign of the acceleration will depend on the coordinate system that you choose. So when I say that, what I mean is that a lot of times we will define up as positive and down as negative. That's our coordinate system. Or we would define right as positive and left as negative. That's our coordinate system. So remember, our positives and negatives are directions. So that's how we're defining them. When I write g, I mean the number, 9.8 meters per second squared. If the coordinate system chosen has up as positive, then things that are falling will have an acceleration of negative g. So I hope that you're seeing that kinematics equations are about to come into play. We got some motion graphs down here. I know you're all super excited about that. So let's look at this. If we look at a graph of motion of a particle dropped with an initial velocity of 0, we would see the following. Well, I know that this has to have a slope which is negative g because it's falling. So I have an object which is here and it's dropped and it's going to go faster and faster and faster. And the acceleration is that way then. So if I say up is positive, then the acceleration is negative g. So if I were to take the slope of this, my acceleration would be the slope of that, and it would be negative g. Now if I look at my position time graph, I would start out at some height, and then as time was going on, I would speed up. So I would get a curve that looks like that. My slope would increase negatively on my position versus time graph. Okay, let's keep going. So as we move on then through free fall, here's another scenario. If we look at a graph where an object is thrown downward with an initial velocity. So now I'm moving downward. I'm throwing something downward. That means it starts with some negative velocity. So we say that's negative v naught. But then it doesn't matter. It's still going to have that slope of negative g. Because once it's under the influence of the force from the Earth alone, then that is the slope of the graph. In terms of my position time graph, Instead of starting flat, now I'm going to start with some slope and then just get more sloped as time goes on. Okay, one more. If we look at a graph of motion for an object thrown upward, so now you're going to take your ball or whatever you have and you're going to throw it upward. So that means I start with some positive velocity, but then remember that as time goes on, again, the slope of this is going to be negative g. So I'm always going to have this negative slope no matter where my initial velocity is. As soon as it's under the influence of the force from the Earth alone, it's going to have that slope of negative g. And then again, I'm going to take my position time graph, and I have a positive velocity first, so I start off with a positive slope. I come to a stop momentarily, so I'm flat momentarily, and then I move back down into a negative slope. So then there's the matching position time graph for the velocity time graph shown. And the slope of this graph at the beginning would of course be v naught, because the slope of graphs, my position time graph will tell me my velocity time, the slope of my velocity time will tell me my acceleration. The time for an object to rise a height h is the same as the time for an object to fall from the same height. So the amount of time it takes to go to h is the same as the amount of time it takes to fall from h. So if I know that's 4 seconds, then that means that's 4 seconds. If I know that's 2 seconds, that's 2 seconds. If that's 8 seconds, that's 8 seconds. So then if I had know the total time, then I know half the time it was going up, half the time it was coming down. The speed of an object at the height h above the surface of the Earth is the same on the way up and the way down, but the direction is different. So, if I say, okay, I have an object and I want to know at this height h. Well, there's 2 points when it's at that height h, both there and there. And at each of those points, the slope is the same, which means the speed is the same. The only difference is that this is positive, this is negative. So it would be like here and here. Notice numerically, those would be the same, the only difference being one's positive, one's negative. The velocity of an object at the very top of its path, so right at the top, before it changes direction, is 0. But notice that the acceleration is still negative g, right? Because if we're looking at acceleration, it's still, the slope of this line is still negative g, even though that point, that 1 point, is 0. Now, think about what would happen if the acceleration wasn't negative g. What if the acceleration went to 0 at that point? Well, if the acceleration is 0, then that means the Earth stopped pulling, and then that means if the Earth stopped pulling, that the object would just float. And if it just floated, it would never come down. And if it never came down, well, baseball would be a whole lot more exciting or a whole lot more boring, one of the two. So keep that in mind. So all of this information is important when we're talking about free fall, and it gives us a good idea of where we should go in terms of how to think about scenarios associated with objects where the only force acting on them is the force from the Earth.